This is a NeuroGuide webinar on the new release and product called swLORETA Neurofeedback. I'm going to have special emphasis on the cerebellum because it's one of the new additions to neurofeedback for EEG biofeedback in comparison to previous neurofeedback methods. Previous swLORETA, that's NF2 in NeuroGuide. It's S because of standardization by Z-scores. Has 88 Brahman areas included in it, but it does not have the cerebellum, nor the red nucleus, nor the subthalamus, nor the habenula. So these new areas have been added, as well as the swLORETA for the assessment as 12,400 voxels, and the method of defining or identifying the center voxel is more accurate with swLORETA because the boundaries are made around Brahman areas, and then the centroid is computed mathematically, so you get a little bit more accurate center representation of each of the Brahman hubs or nodes. As always, the important thing is to begin with symptoms and clinical history, and based on the symptoms and history, form hypotheses as to which networks are likely linked to those symptoms. For example, attention problems, then you do a Google or a National Library of Medicine search, and then do with the search terms asked attention brain networks or networks related to attention, and you will find the huge literature in the Human Brain Mapping Program, $2 billion the first decade, $2 billion the second, and the third, etc., has given rise to thousands and hundreds of, if not thousands, of papers on functional MRI, PET scans, SPECT, EEG, and MEG, with a common coordinate system that was established in the 1990s, referred to as the Thalaric Atlas coordinate system, that has a linear transformed to the Montreal Neurological Institute's coordinate system. They're really the same with linear transforms. That allows there to be co-registration of different imaging modalities. SPECT scans, PET scans, functional MRI, EEG, MEG, all can be co-registered. That was well established in that National Institutes of Health in the 1990s. Is now the standard. So it allows one to search this vast literature using the internet or whatever method you want to identify the hubs and networks in the brain linked to different symptoms. Then you do an assessment of the brain itself with quantitative EEG, diffusion tensor imaging, MRI, PET, whatever, to make a link between the patient's symptoms and the networks of the brain that may be dysregulated and linked to the symptoms. Then you devise treatment. It can be a variety of different treatments: neurofeedback, brain-computer interface, light therapy, DCS, medication, etc., RTMS, as long as that linkage happens, and then you reassess the progress to see to what extent the patient's symptoms are reduced. This is just another illustration of the same concept, where you start with symptoms, you then create hypotheses about which networks are likely to link to those symptoms. You then launch NeuroGuide. You then record EEG using good collection hygiene and editing, and make sure that you get rid of artifact. And now that you have the hypotheses about symptoms, or the parts of the brain likely linked to symptoms, you then do spectral analyses and confirm or disconfirm those hypotheses. And then you devise a neurofeedback protocol based upon that linkage of the patient's symptoms to hubs and networks in the brain. You can use NF1, NF2. Now we have swLORETA neurofeedback. It's the topic of this webinar, brain-computer interface with the brain surfer. Then you have session charts and Neurostat to evaluate the efficacy of your treatments. Now what's new is the fact that we're using swLORETA. The old school is Loretta, that was developed in 1994 by Roberto Pascual Marquis. He was working at the Key Institute in Switzerland at the time. This is called the Key Institute Loretta as a consequence. He used the Montreal Neurological Institute's MRI that was available at that time, which was an average of 306 individuals, and you can see on the left that there's no clear gyri in this viewer. You do have the standard telluric atlas system and Montreal neurologic coordinate system and Brodmann areas, etc., in the box on the right. And it's an excellent navigation and viewer tool that was developed by Roberto. But now it's outdated. Today, there are operating systems and computers that won't run the old Key Institute viewer. And it lacks resolution. That's 2,394 voxels, as opposed to the one on the right, which is swLORETA with 12,400 or so voxels. We use swLORETA for the old Loretta because by dividing the source space by the standard deviation. That standardizes Loretta. That's why it's called swLORETA. swLORETA on the right, which shows very clear gyri and details of the MRI. This uses the Montreal Neurological Institute's template brain called the Collins brain. Anybody can download it and use it. It's a standard in the field, but it gives you much higher resolution. Raw Loretta uses a spherical head model, but the brain is not shaped like a sphere. It's more shaped like a loaf of bread that's flat on the bottom and elongated. So swLORETA was developed as standardization. As I mentioned, you take the standard deviation of the source space and divide it into each of the voxels. That helps minimize the error of the spherical head model. You also use what's used in SPM for functional MRI, the variance of the F distribution of the variance of the sources to increase the accuracy. Z-score Loretta, as I mentioned, is swLORETA because it divides the source space by the standard deviation. But it's just the standard deviation in the case of Z-score Loretta version of swLORETA is the standard deviation of the subjects at a given age across subjects, but nonetheless it's a standardization. swLORETA, it's called weighted swLORETA, does the standardization that swLORETA does, but with more voxels, in this case 12,470. It uses a realistic MRI, not an average, and the boundary element method, in which one can, and not the spherical head model, in which one can create a boundary around the surfaces of the brain, and then using Green's function and other 1800s methods, you can calculate the lead field and the forward solution that was developed in the physics in the 1800s. It's also works on modern computers, and it's capable of being platform independent, and it has excellent customer support. And that's why its replacement of the old Loretta is one of the reasons also that it's so useful. So in conclusion, swLORETA improves the localization properties of the swLORETA method. swLORETA is able to reconstruct sources under real conditions in the time and frequency domain, and therefore be used for neurofeedback, and it's an excellent replacement for the old Key Institute. Now, an issue, one of the great things about the boundary element method and the weighting that swLORETA allows you or provides is that you can get greater depth of sources with high accuracy. And so briefly, I'm going to go through the cerebellum neurofeedback feasibility. The feasibility of doing the regular 88 Brodmann areas, there's no doubt about that. There's numerous papers published and in functional MRI and EEG neurofeedback. One thing that's important to keep in mind that there are over 40 million people over the age of 65, and many of whom have balance problems and vertigo and dizziness. There's also about 11 million people with Parkinsonism and about 16,000 new diagnoses per year. Also, we know that the cerebellum is involved in cognition. It's related to problems that people have with traumatic brain injury and language, and a variety of other things. When I was at National Institutes of Health as the project manager for the first 128 channel EEG, we noticed in the PET scanner that the cerebellum would light up under a variety of different conditions that we actually did not expect. They were not motor conditions. There would be face recognition tasks, language tasks, memory tasks, emotional tasks, looking at faces with different emotions expressed, etc. And the cerebellum would light up. We had numerous meetings to try to understand that, and came away with the understanding that the basal ganglia thinking itself is a type of a motor operation that's unique and special, language as well, involving the boundaries of populations of neurons in the basal ganglia, but the cerebellum is involved in helping to coordinate that. Also, autistic spectrum disorder, there's a number of papers showing that cerebellar circuits are involved in autism spectrum disorder, and I'll be briefly showing that as well. Part of the feasibility of all this, as I mentioned, at the National Institutes of Health, we're able to compare the time resolution and spatial resolution of different imaging methods. The x-axis here is time in milliseconds, and EEG is down to about 1 millisecond. And the spatial resolution, the best you can do is roughly right around 1 centimeter. Functional MRI can get down to maybe 5 millimeters in special circumstances. But the brain actually operates in large collections of billions of neurons. Usually Brodmann areas themselves are on the order of centimeters, not millimeters. And so large collections of neurons become synchronized for brief periods of time, let's say 250 milliseconds, and a different group of neurons are recruited across the various hubs of the brain. They become phase locked, they mediate a given set of functions, and there's billions of them distributed across space, operating quickly in time, phase locked. Then they are dispersed and another set of neurons are recruited, and this continual process of phase shift and phase lock is going on to mediate functions by recruiting large numbers of neurons, locking them in for brief periods of time, and that is a very efficient way to process information in a healthy brain. This is a summary of 30,000 functional MRI studies by Laird et al. In 2011. And you can see that there's clusters of different parts of the brain that light up in PET scans and functional MRIs. This is reviewed in the Handbook of Quantitative EEG and EEG Biofeedback. I won't go into a lot of detail, except the number 14 is the cerebellum, and some of 19, number 19 is the cerebellum. So the cerebellum is one of those structures that's part of the human brain mapping program, referred to in this case, the intrinsic connectivity networks, ICNs, which are also inside of Neurogun, so you can select these various ones if you wish. There's also a large number of EEG cerebellar studies. If you do go to the National Library of Medicine using PubMed and use the search term cerebellar EEG, there'll be 2,536 citations. That was the case in October. There's probably more now. And you can go through there. There's quite a few studies on the ability to measure EEG from cerebellar sources with electrodes on the scalp surface. It used to be thought that you can only measure that EEG is only produced by pyramidal neurons, but it turns out that's not the case. The resolution is not as high as it is with the cerebral cortex. But nonetheless, one can, using particularly boundary element method and by homogenizing the lead field, which I'll be showing in a minute, allows one then to get deeper source resolutions and more accurate ones, as shown in the scientific literature. This is just an example of another one of the papers on cortical connectivity and stroke patients using swLORETA for the cerebellum. Here's swLORETA in individuals who are moving or imagining moving their left or right arm to a given point in space. And as they do, you can see the cerebellum lights up. These are this is EEG current sources measured by electrodes on the scalp surface in healthy behaving individuals, and alpha, theta, beta, and alpha, beta ratio bands. And so it's established clearly that you can measure cerebellar EEG sources using swLORETA with electrodes located on the scalp surface. Now, cerebellar neurofeedback validations, in this case, we look at it in more detail, a study was done looking at SMR neurofeedback in 2 groups of monkeys. Both groups had their dopamine and dopaminergic neurons degenerated chemically, and thereby inducing Parkinsonism. And one group got sensory motor neurofeedback, that is at 12 to 18 hertz. The sensory motor rhythm, or it's also referred to as a mu rhythm, appears when animals inhibit movement. And so Barry Sturman is one who helped develop this method. So did Joel Lubar, Michael and Linda Thompson, and numerous others have published papers on sensory motor rhythm neurofeedback. Michael Thompson and Linda Thompson published a paper with Parkinsonism and showed that it had improved or reduced symptom severity. In any case, this same the parallel study by Philippines was conducted both on humans in a different publication, but in this case with monkeys, in which they induced Parkinsonism. And the circuit we're most interested in is the one on the right, but the one on the left shows you the basal ganglia and involves dopamine D1 and D2, where degeneration of the dopamine results in inability of the substantia nigra and the subthalamus to coordinate and communicate with the dopaminergic system, and thereby the control mechanisms for limb control and stability are lost, and tremors emerge, first especially in the hands and then in the trunk with time. On the right is a parallel motor circuit from the cerebellum that does not involve dopamine. This is involved more in the gait motions when one walks, rather than the fine motor movements of the fingers when one writes. The movement as you stand and you swing your arms and your legs is mediated largely through these large cerebellar circuits that are communicating with the basal ganglia, where commands for movement are initiated, and the cerebellum with 80 billion neurons more or less smooths that out. Citations to the literature are listed below. And they found that with neurofeedback, that there was quite a large proliferation of neurons and connections in the red nucleus. Now, the red nucleus is a relay nucleus from the cerebellum. Cerebellum outputs to the red nucleus to the subthalamus, subthalamus to the thalamus, thalamus to the cortex. Okay, that's that circuit I just showed. So there's the red nucleus is going to the thalamus I show here, but it also goes to the subthalamus to the thalamus. Now, so there clearly is a change in the number of neurons by SMR neurofeedback in monkeys, and in fact, the severity of the Parkinson's symptoms went down as a function of the neurofeedback, and had cytological confirmation of the effect of neurofeedback, SMR neurofeedback, on the symptoms and on the brain itself in terms of its connectivity, in which the cerebellar circuits is a compensatory circuit. And to the extent to which that circuit becomes more active, then the severity of the symptoms goes down. That helps explain the findings of Thompson and others, showing reduced severity of symptomology in Parkinson's patients after doing SMR. Now, this is the Neuronavigator. We have had a lot of images on that and videos. This is just another one that you can do. Anybody can do these kinds of things. Now, this is an example of the real-time Neuronavigator. On the right is the connectome, The right hemisphere is the right part of the circle is the right hemisphere. The left part of the circle is left hemisphere. The top is the frontal lobes. Bottom is the occipital region. Now we have the cerebellum included in this. And these are different networks inside the navigator. And we have other videos and webinars on this. Here's the real-time Neuronavigator. We use this for this is swLORETA. swLORETA is an engine that's inside of the Neuronavigator, and we use this to do the neurofeedback. And these are the circuits. For example, this is the vertical circuit on the left of the cerebellum to the motor cortex. And on the right is an example of the Neuronavigator in which we've selected Bravo areas 1, 2, 3, and 4. That's the sensory motor cortex there at the top. And the bottom is the cerebellum, Sub-Thalamus, and red nucleus. This is the anatomy of the cerebellum. I recommend that people do a search on the internet for cerebellar lobes and areas, and you'll learn a lot about the way this 80 billion neuron structure operates. It's quite interesting. It's a very, very important part of our brain. This is just another example with you can create protocols. We're going to for neurofeedback using the navigator. I'll be briefly showing that. Then you can look at the patient's EEG and connectivity using the Neuronavigator, looking at coherence, phase differences, lag coherence, and information flow using the phase slope index. And there's different views. You can turn the brain around and look at it if you wish in whatever way. As you link the patient's symptoms to dysregulation and hubs inside the brain to create a protocol for swLORETA neurofeedback. It's just another view of the same thing. The top there is the sensory motor cortex, and the bottom is the cerebellum, and you can also overlay diffusion tensor imaging, and you can color the diffusion tensor imaging fibers depending upon the deviation from normal. It's just a way to see the Neuronavigator, and it's useful to rotate the navigator as you're evaluating the parts of the brain. You can see at the top there the sensory motor cortex is red, and those are close together circuits. This is essentially a small world model. That is, the blue shows low connectivity and low information flow compared to the local circuits. So short distance local circuits are highly interconnected, and there's reduced connectivity over the long distance circuit. But that's well balanced in a healthy brain between the ability to process information locally and communicate over long distance fiber systems to other hubs and clusters in an efficient manner. Now, recently there was this excellent paper on cerebellar circuits and autism spectrum disorder. I recommend people look at this paper. It's in Frontiers in Neuroscience, Volume 9, page 408. Go ahead and pause this video if you want and take a look at this interesting study. They used functional MRI to look at an autism spectrum disorder and found that the cerebellum was significantly related to the severity of the symptoms, and also their cerebellar cortical interactions. For example, supplemental motor area, the inferior frontal gyrus, the superior temporal gyrus, or some of the regions, dorsolateral prefrontal cortex, premotor cortex, etc., for cerebellar involvement in the severity of the patient's symptoms. They then mapped out the parts of the cerebellum by different colors that co-varied with different parts of the hemispheres. Left and right hemisphere and the medial right, medial left hemisphere gives you an idea of how the cerebellum communicates and has functional connectivity with these parts of the cortex. So cerebellum is not limited to just the motor cortex. But right now, we're just going to focus on the motor cortex to make it simple but you can design any protocol you want in swLORETA Neurofeedback. This is what they came up with for the different aspects or dimensions of autism spectrum disorders, for example, stereotype behaviors and repetitive behaviors, motor impairments, affective dysregulation, social processing, irritability, language problems, social cognition deficits, face processing impairments. These are some of the problems that children in the autistic spectrum disorder have problems with, but now the neuroscience is able to link the cerebellum to the cortex and to these categories of symptomology, which gives hope that conceivably with swLORETA, working with autistic spectrum disorder children, that one can reinforce greater stability and efficiency in the cerebellar and cortical hubs and the cerebellar and cortical functional and effective connectivity to move the brain towards a healthier, more efficient state and thereby potentially reduce the severity of the symptoms. We are currently conducting a variety of different studies. We're making good progress. We've looked at TBI and other issues. We're going to be looking now at neurofeedback. These are Romberg tests where one moves their finger, right finger to the nose, left finger to the nose, etc., while we record the swLORETA from the cerebellum and the somatosensory cortex. We find highly significant changes from baseline to when people are moving. And especially in the line coherence, this is here we stimulate with TDCS, direct cortical stimulation, and placing the anode and the cathode in a balanced manner, left and right hemisphere, and reversing the anode and the cathode, and seeing the effects it has on the cerebellum post-stimulation. So it verifies that we can measure EEG sources from the cerebellum. We also did a discriminant analysis on mild versus severe TBI and got 93% accuracy. Cross-validation was 89%. Normal versus severe is 99% accuracy with a 97% cross-validation. So this is using the cerebellum and the sensory motor cortex in normals and severe TBI and seeing if we can discriminate these groups. We also could do mild versus severe and normal versus severe. So the cerebellum can be used to evaluate or at least correlate with symptoms and the severity of the symptoms, such as traumatic brain injury. This is just an example of the plots we get when we do these studies. And this is the menu that you will see inside of the Neuronavigator when you do swLORETA Neuronavigator, and also when you do swLORETA Neurofeedback. This is the panel from swLORETA Neurofeedback, in which you can select the cerebellum, the different parts of the cerebellum. You can also select the anterior or posterior lobule. You can select functional groupings, such as the grouping involved in balance and motor movement and ataxia. We've also added the cerebellum to other areas based on the scientific literature, such as autism spectrum disorder and anxiety. And so we've modified the networks inside of NeuroGuide. So when you do swLORETA Neurofeedback, it's an updated modern application or addition to Neurofeedback, in which you can evaluate the patient first, create a protocol, and then begin to do neurofeedback. This is an example of the first time that cerebellar neurofeedback occurred. It was at ISNR in September of this year, 2019. And we were able to do that. And this is an example, and I'll be showing this in a minute, of cerebellar neurofeedback. We're actually doing cerebellar neurofeedback on the sensory motor cortex and the cerebellum in this volunteer. And we're able to change the brain within a few sessions. So I'm going to move over now to the examples of, to the mirror guide itself. I'm going to close this out and bring up, here's a patient, for example, and you can evaluate that patient. As you know, there's plenty of examples of doing this. After I've edited out in the artifact, evaluate the patient, I save data in the patient's folder. In this case, this is the demo patient who was assaulted, struck in the right hemisphere. It's paralyzed on the left. And now you got a clinic report, and you can link patient symptoms to the patient's brain. There's disconnection in the right parietal region. These are red are largely compensatory. We have a lot of webinars on that. You can save this, of course. And you can also launch swLORETA, which I've done here to save some time, and evaluate the same things in much greater detail. And move around inside the brain. You'll see the cerebellum here is actually significantly deviant from normal. Red here is greater than 2 standard deviations. So this is the cerebellum. It's much more deviant from normal on the right than the left. Cerebellum crus 2, for example, right, value is 4 standard deviations. You can see a little bit more at 5 hertz is where he's most deviant from normal. You can see that right parietal lobe is deviant. I'm going to remove the cortex, and these are the deviant coherence. Here's information flow, phase differences, lag coherence, etc. These are z-score deviations from the cerebellum versus the sensory motor cortex. And the scale for deviation from normal is there. Now, if you want, you can go to export, and you can export a protocol there. The standard method, though, is to go to report and generate, after you've done a complete analysis and link patient symptoms to the brain, so you're ready to create a symptom checklist match. I can go there and create a symptom checklist match, which I've already done. And so what I'm going to do now, instead, I'm going to just close down this Neuronavigator and begin neurofeedback with this individual. So I've done my evaluation, and I'm going to do setup and monitor. I'm going to do a playback, but this could be your patient that you are running. This is our demo patient who was struck in the right parietal region and definitely has motor problems. This is the EEG, and this is where you do neurofeedback. I'm going to go to collection. This is the NF2 swLORETA. This is the new swLORETA neurofeedback. We're going to do surface neurofeedback. We also have cross-frequency surface. In the future, we'll have LORETA cross-frequency. So I select swLORETA. You can create your own protocol right here. You see the cingulum, the cerebellum, and all the various parts of the brain. So you can manually create whatever protocol you wish. I'm now going to go to my symptom checklist that I just created. I did it really fast. I mean, I already done it. Had already done it, so I didn't want to waste our time. That's where I went to report swLORETA create symptom checklist match. I saved it here, and I created an SW neurofeedback.sws file. That's for the symptom checklist. So I load that in, and now I'm going to go to networks, and let's take a look at balance, for example. These are the areas we've selected for our protocol, the vermis, Brabant areas 1 through 4. Those are most important for balance. Motor movement is more on the lateral lobules of the posterior cerebellum. And so I'm going to say, okay, I'm going to be looking at phase differences, lag coherence, coherence and power. And I'm going to say OK. And I'm going to set the threshold for, in this case, it's a little high because I've already done this. I'm going to do Z-tunes. Z-tunes is giving you reinforcement when the outliers are moving in the direction of Z equals 0. We have a lot of videos on that. It's a standard protocol. This is no different than what you've seen before. If you want to see which variables were selected, you just click that. There's 1,360 variables were selected. Okay, and now I'm going to begin session. I'm using the CZ head, but you can use DVD players, the ANI streamer, progress charts. There's all kinds of things you can do, but CZ head is I'm going to use for now. And I'm going to begin the session. And there's the neurofeedback occurring. I'm going to get rid of this message. And there's where you move that over to the patient's screen. So the patient now has the job of keeping the green light on, or if it's a DVD, keeping the DVD going. We'll look at the number of scores. Right now there's 12. You want to get 20 to 30 feedback signals per minute if you can. But right now, if this was a patient, we would be doing cerebellar neurofeedback for an individual with balance problems. We can select other ones. We can do the cerebellum directly. We also have the autism spectrum disorder. We can do it there as well. So I wanted to show you how you do that. The rest of it is pretty much the same as what we did in the past. Everything else is the same. It's an easy thing to learn. It's pretty much the same. Those of you that are experienced in NF2 and NF1 neurofeedback, the surface and swLORETA, you'll find it's essentially identical. The difference is now we have the cerebellum, habenula, sub-thalamus, and that with connectivity and functional connectivity and effective connectivity. We also have the neuronavigator to help you link symptoms to dysregulation in hubs in the brain in a much more powerful way. So thank you for watching.